How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at 5.6 Hess's Law. So our objectives will be to apply Hess's Law in order to determine the change in enthalpy, or delta H, of a reaction given the delta H for other reactions. So, quick review, state functions. Remember that state functions only depends on the state of the matter, not how it got there. It's kind of like a change in altitude. Right? So let's say that you were on a hike in the Grand Canyon and you wanted to know the change in altitude. Well, maybe you're starting way down here and you have to hike all the way up. Well, here's my destination. Doesn't matter if I hike up this way and go that way and then this way and then that way and that way, or just straight beeline it and climb straight up that mountain. No. So it doesn't matter because all the change in height is, or the change in altitude, is going to be equal to, the altitude, which at your finish minus the altitude that you started at, right? So it doesn't matter what route I took. If I took the curvy route or if I went just straight up the mountain, it doesn't matter how I got there. It just matters, where I started and where I ended. It depends on the state, where I'm at. That's all that matters. So delta H is a state function in the same way. It doesn't matter the path you take. It just matters the overall change. So if you know the delta H for the steps in between. So like, let's say we wanted to know, all right, well, what's the change in the energy from A to Z? If energy was this y-axis, how could we figure that out? Well, if we went from A to B to, C and then Z, and we knew the change in heat for each one of those steps, then we can figure out what the overall change was from A to Z, right? So you can figure all that out. So Hess's Law states exactly that. If a reaction is carried out in a series of steps, the delta H of the reaction will equal the sum of delta H's of each step. All right, so like I was saying, if I went from A to B and then went B to C and then C to Z, and I went, all right, well, this is going to be reaction 1, this is going to be reaction 2, and then this is going to be reaction 3. Well, what is the delta H for this reaction? I'm going to call that, delta H A to Z, right? So the change in enthalpy from A to Z is going to equal the delta H of reaction 1 plus the delta H of reaction 2 plus the delta H of reaction 3. If you just add all those together, then you would get the overall change. So before we begin, I want to talk about what happens to the delta H if we do a couple things to the equation. So let's say that this was my equation. I have this reaction, and it tells me the delta H for that reaction is exactly this, right? So what would happen to the delta H if we flip that equation? If instead of having, carbon solid reacting with oxygen giving me CO2, if it was the reverse of that? Well, if it was the reverse of it, what would happen to the delta H? Well, if the forward reaction gives me negative 393 kilojoules, if I went in the opposite way, then it's just going to give me positive 393 kilojoules, right? That's it. So what happens if I doubled the equation? So instead of just carbon and oxygen, one of each, everything was doubled. What happens to the delta H? Well, it's going to be equal to whatever it was originally times 2, because I'm doing it twice. So you are going to get, let me get some numbers real quick. That's almost 800. So it's 700 and what's it, 84? No, 86. So it'd be negative 786 kilojoules because you just double it. All right, well, what happens if we flipped it and cut it in half? Well, let's think about it. If it looked like this, flipping it, flip means, change the sign. Change it from positive to negative or negative to positive. And then whatever you do the coefficients, that's what you do to the value. So if I flip it, well, I need to make it a positive 393. And if I cut it in half, I got to divide that by 2. And if I can do some quick math in my head, that'd be like, I don't even know, positive 196.5 kilojoules. All right, so what these problems are going to look like when you have a Hess's Law problem, it's going to look like you're given a target equation. Like this is what you're trying to get overall, and then they're going to give you some known reactions. So these are reactions that they'll give you, and they'll give you the delta H's for those. So what do you got to do? Well, what you're going to have to do is you're going to have to look first at the target equation. So first thing is look at the target equation. Boom, found it. That's what I'm trying to get. Secondly, find reactants and products in the known equation. So I'm looking to get carbon as a reactant. Hey, look, I found carbon as a reactant here. I'm trying to get hydrogen, H2 as a reactant. Hey, I found hydrogen in that reaction. And I'm trying to get CH4 as a product. Hey, I found it right there. So next is you might have to rearrange some of these equations as needed to get the things to where they need to be. So in this example, I didn't give you anything you had to rearrange because look, hey, carbon's a reactant here, it's a reactant there. Hydrogen's a reactant here, reactant there, and CH4 is a product here, and it's a product there. So hopefully we just have to add all these together. All right, so if I had to flip them, then I'd have to adjust the value of the delta H. If I flipped it, I'd have to change the sign. If I doubled it, I'd have to double the delta H, so on and so forth. But if you take a look at these examples, what it's saying is, all right, well, if this is my desired reaction, I can have that happen in these 3 steps. So hopefully, if I add all those reactions together, I will get this overall reaction, right? So let's see what happens. Well, I have carbon plus O2 giving me CO2. Is there anything that can cancel out? Well, hey, CO2 here, there's a CO2 there, it's going to cancel out. It's on the product side, and the reactant side, it drops out. I have, let's see, H2O. I have 2 of them, and I have 2 H2O down here, so they're going to drop out as well. And then I look, all right, is there anything else that can cancel out? Hey, I got 2 O2. I have 1 O2 here and a second one there, so the O2 drops out. And what happens when I add all these together? I get carbon plus hydrogen. 2 hydrogen gives me CH4. So what you're going to do now is whatever you did with the equations, you're going to do with the delta H's. So I just added them all together, and I'm going to do that here. So when I combine these 3 numbers, I get a negative, I get a negative 73 kilojoules. So that would be the overall enthalpy change for that reaction. It's going to equal negative 73 kilojoules. So that's all you got to do, right? So conceptually what's going on is it's just like the altitude, like I was saying. The change in the altitude doesn't matter what path you took, just the beginning and the after. And if you add up all the altitude changes for each step, you'll get the overall change. And that's what you're doing right here. You're taking a look, all right, well, if I did this reaction, this is how the enthalpy changes. And then if I did this reaction, this is how it changes. And if I did that last reaction, this is how it changes. So if I want the overall change, if I want the overall delta H, I got to, add up all the delta H's for the, contributing reactions. So that's what you're doing. But it's not always as easy as that example. I started with a really easy one where you didn't have to do anything to the equation. So let's say that this was my equation, and then they gave me these 2, possibly steps to do it. Well, I'm going to follow the same process. I'm going to look at my reactants and my products in the desired equation, and I'm going to try and find them in the other given equation. So I'm looking for IF5. I found IF5 right here. I found IF3. I found it in this equation. I'm looking for F2, and I see F2 in a couple of places. So let's start rearranging things as needed. I need IF5 to be on the reactant side. Well, in this equation, it's on the product side, so I'm going to have to flip this, right? Which means my delta H is going to change sign. It's going to go from a negative to a positive, and my reaction is actually going to be, IF5 becoming IF and 2 F2s, right? So now I can ignore this because I flipped it around. So let's see, I need IF3 as a product. That's where it is. I need F2 as a product. I have F2 over here as a product. Hopefully now I can just kind of combine them. So let's see if things cancel out. Well, I have an IF here and an IF there. They're on opposite sides of that reaction arrow, so they are going to cancel each other out. I have 2 F2s on the product side, and I have 1 F2 on the reactant side. So I can cancel out that 1 F2, which is going to leave me with 1 F2 over there. And hey, look, IF3, that's still there on the product side. So F2 plus IF3. So everything canceled out, which gave me my overall reaction equation, which is what I wanted. So now what do I got to do with these delta H's? Well, I already did everything I needed to, so I just got to combine them. And if I press some buttons real quick, let's see, negative 390 plus 745, I get a positive 355 kilojoules. So the delta H is going to be 355 kilojoules. Let's try another one. So here's a equation, and then here are some equations that we know. This time there are 3 of them. All right, so but you're going to do the same thing. I love these things because they're like little puzzles, like Sudoku puzzles or something. So I need 6 carbons on the reactant side. Let's see if I can find carbon anywhere. The only place I see carbon is right here. So that means I'm going to have to, hey, wait, I need 6 of them. This reaction only has 1 of them. So I'm going to have to times this by 6, right? So I end up with 6 carbons, 6 oxygens, and 6 CO2s, which means what do I got to do to the delta H? Well, I got to multiply that by 6 because I did it 6 times. All right, what else do I got to do? All right, well, let's take a look. H2. Do you see H2 anywhere? I see H2 right here. It's on the reactant side, which is where I needed it, but it says I need 3 of them. So let's see. I'm probably going to have to triple this equation. So instead of 3 halves, or 1 half, I'm going to get 3 halves, and I just times everything by 3, which means that this delta H I need to times by 3 as well. Now, the last thing that I need to do is, all right, well, C6H6 as a liquid. Do I see that anywhere? I sure do. It's right here, but it's on the wrong side of the equation. I need it as a product. I have it as a reactant, so I'm going to have to flip this equation, which is going to change the sign of this delta H. So let me rewrite this, right? So I'm going to get 6 CO2 and 3 H2O, giving me C6H6 and 15 halves of O2. I'm going to clear some of this up real quick so I don't get too crowded. All right, so that's what my equation becomes when I flip it. I already changed my sign. So now hopefully when I combine these equations, I get what I want. I get that equation. So let's see what happens. Anything can cancel out. Probably I got 3H2O up here, and I have 3H2O on the other side, right? 3H2O as a reactant and product, cancel out. Let's see, what else do I got? Do I have O2? Well, let's see, I got 15 halves of O2 up here as a product. I have 6 O2s here, which would be 12 halves. And then I have 3 halves O2 down here. So that cancels out all 15 halves of the O2. And I think that canceled almost everything out. Wait, oh no, the CO2. I have 6 CO2 here and 6 CO2 there. So if it's on the reactant side and the product side, I can cancel them out. And what am I left with? Well, I'm left with C6H6. I'm left with 6 carbons, and I'm left with 3 hydrogens. So I end up with 6 carbons and 3 H2s, giving me a C6H6. So now that I adjusted my delta H's, I got to start doing that math, right? So I'm going to do... All right, so now that I did the math and got all those things, now all I got to do is add them together. So we get a positive 3271 kilojoules plus the negative 2364 kilojoules, and then plus the negative 858 kilojoules. And I end up with a final answer of 49 kilojoules in the positive. Boom. So that would be my final answer. All right, so summarize. What does Hess's Law state, and how does it apply to chemical reactions, and how do you solve these Hess's Law type problems? Hope you found this helpful. I'll see you in class. Bring questions. Okay, bye.